next speaker we have with us is Vanya Jauhal. She's from Google, Sydney, and she has worked there for the past 2 years. She graduated from IIIT Hyderabad, and she has hiked in 8 different countries, and she's a hiker. She loves anime, and she's from the army background. And the topic she's going to speak for today is safe client behavior. So I request all of you to please welcome her with a big round of applause.
Hello everyone, I'm Vanya Jauhal. I work for Google Maps. With a quick show of hands, how many people here have used Google Maps in the last few weeks? Excellent choice of product. So in order to answer the queries that you guys make, we have a bunch of servers running on the cloud. But where does the client behavior affect these servers? It turns out that client behavior can be a major factor affecting the reliability of services. And even some of the most carefully clients can bring a service to its knees. Which brings us to the topic of today's discussion, safe client behavior. Now, when I think of client-server interaction, something like this pops up in my head. We have a server, and a client sends requests to it. But this is not how things are in the real world. We have 2 billion monthly active Android devices. How many servers do you think we have? 2? 20? 200? Even if it's 2,000 or 20,000, that's far less than the number of clients. So in the real world, this is what things look like. We have a bunch of servers and a whole lot many clients talking to them. Number of clients is orders of magnitude greater than the number of servers. And because there are so many more clients than servers, the rules for safe client can be summarized as do not DDoS. DDoS is distributed denial of service. It occurs when multiple systems target the bandwidth of one particular system. Now, I don't think any client developer intentionally tries to DDoS. Or that's what I hope so, unless you hate your company or something. But it's hard to reason what millions of clients acting independently would behave like. But which requests are unsafe? Or should I say, potentially unsafe? User-generated requests are usually not a problem. There's only so fast a person can click. Dangerous are automated requests, like startups, retries, and periodic requests. OK. So we have a few dangerous requests out there. What's the worst that can happen? Bad things happen. Your data center would not literally catch fire, but it's still a pretty unpleasant situation to be in. And misbehaving clients have known to cause server outages in the past. What is the best that can happen? So this graph represents an ideal server-side request pattern. The blue line is successfully served requests, and the red line represents errors. For an ideal pattern, we should see no errors, oscillations, or spikes. And this brings us to our rules for safe clients. For the following slides, I would assume that we have a client that sends a request to the server every 5 minutes, say, to check the time. Rule 1, jitter everything. Jitter means the deviation of true periodicity of a periodic signal. Or in other words, add randomness to the periodicity of a signal. Let's consider this code. We have a client that sends requests to the server every 300 seconds. What does the request pattern for this look like? We see that the load spikes up every 5 minutes. Axis labels are intentionally left out in this case because we are more interested in the shape of the curve than absolute values. Now, this type of request pattern is obviously bad. Load is spiking up every 5 minutes, and the servers are idle for the rest of the time. So our rule was to add jitter. Let's try jittering the periodicity of our code. The client chooses a period between 2.5 to 7.5 minutes. Earlier, it was just 5 minutes. The effective periodicity of the signal still remains the same, but the actual period is picked up every time, every execution cycle by the client. What does this look like? We see that the load smooths out fairly quickly, and we get an almost nice flat curve. But do you notice? There's still a spike in the beginning. Why is that? So even though we jittered the period of our signal, the startup is still synchronized. Okay, why is synchronized startup a problem? It's not like all clients send requests at the same time, right? Well, sometimes external events can lead to unintentional synchronization. For example, if you have an app that turns off data every night and switches it back on at, say, 4 a.m., all the clients in that time zone would flood the servers at 4 a.m. So let's try fixing this. We now jitter the startup time as well, and we can see how it behaves. This is good. The startup spike is gone. But we have some oscillations in the beginning. Where's that coming from? And what can we do to fix it? I'll let you guys take a few minutes to think about it. A few seconds. So when we jitter the period of a periodic signal, overlapping periods lead to oscillations. In this graph, each colored line represents the probability of a signal being sent at that time. Initially, the overlapping periods are causing oscillations, but eventually enough of them overlap to smooth things out. This is usually not a problem because the oscillations are not very much, and eventually it's smoothing out, but let's try to fix it. In order to fix it, we jitter the execution time instead of the period. To do that, we would truncate the epoch to the nearest multiple of the period and then add randomness. So let's say the current time is 3 seconds and our period is 300 seconds. On truncating it to the nearest multiple of the period, we get 300. And the client chooses a random time between 300 to 600 seconds to send the request. What would that behave like? We get a nice smooth flat curve, and as discussed earlier, this is our ideal case scenario. But I'd urge you all to be careful of this particular case. What happens if we swap around just 2 lines? We end up throwing away all the randomness and end up causing synchronization. And that looks like this. Now, that's a very easy bug to cause. It's just 2 lines swapped around, and it's also very hard to test for. So please be careful of this case. Moving on, the second rule is don't retry. Terms and conditions apply. The current RPC frameworks make it very easy to do retries. And it's actually really attractive because retries help improve the reliability of a system in the face of unreliable backends or networks. But retries should be done very carefully, and the default should be do not retry. Let's consider this code. We have a client that sends a request every 300 seconds. If the request fails, it retries every 10 seconds. How would that behave? So here, the red line represents a server outage and a request spike due to it. And we see that with our retry profile, even with a smooth startup, it leads to synchronization. This is because server outages are seen by all clients at the same time, and all the clients react in a similar way. Now, from our previous rule, we learned that whenever you see synchronization, jitter is a good thing to try. So now we try adding jitter to the period of this signal. How do you think that would behave? We see that even after the server outage, the load smooths out fairly quickly, so that's awesome. But there's another time that we could have jittered. What about the retry delay? So now we try adding jitter to the delay of the retry instead of the periodicity of the signal. And that acts something like this. We see that that doesn't really help very much, and we do, in fact, have to jitter the period. Rule number 3. If you retry, back off. But why? Sometimes server outages can be due to out of quota. In which case, if you keep retrying, you're not helping anybody, and the server is probably just getting more overloaded with your retries. If we revisit our previous case, we see a sharp rise in the request rate when the server stops responding. In order to fix that, we would use exponential backoff. I'm sure you guys are already familiar. The idea behind exponential backoff is to use progressively longer wait times for every time our request fails consecutively. Let's see how this would behave. We see that the request spike goes down by 10 times, and the load actually drops over time. But there's still some blockiness. In order to fix that, we should add jitter to the retry delay. Wait a minute. In our previous rule, we learned that jittering retry delay isn't very helpful. Well, it turns out that when we use exponential backoff, the retry delay becomes bigger and bigger, in which case it makes sense to jitter it. And this behaves something like this. We see that the backoff is smoother. But are you noticing one more thing? The request rate never really recovers fully. Why is that? It's because some clients end up waiting really long times for their retries to be processed. A solution to that can be capping the delay for retries. So, if your retry delay exceeds a certain limit, just drop that request, and then wait for the next RPC. And with that, we see that the request rate recovers, and we get a nice flat curve. So let's revisit some of the terms and conditions for retries. Don't retry by default. If you retry, use exponential backoff. Jitter your delay times if you're using exponential backoff. Retry on specific error conditions. Don't retry on client errors. If your request is bad, no matter how many times you send it to the server, you're not going to see a different response. Do retry on server errors. There might be a case that the server is just facing an outage, and if you retry, the server can respond when it recovers. Do retry on network errors. If the server never got a chance to look at your request, then it couldn't have responded. Retry on timeouts, but do it carefully. Because there might be a case where your request is so big that the RPC times out before the server gets a chance to complete it. And don't retry on out of quota. So far, we've talked about complete server outages. But what about partial failures? Let's consider this case. We have a client that sends a request to the server every 300 seconds. If the request fails, then it retries every 10 seconds. On the server side, there's a 25% failure rate. And you can see how that would behave. The error rate spikes up steeply and stabilizes at a very high level. In order to fix that, we should use exponential backoff. We see that the error rate subsides. But there are still some spikes at powers of 2. This is because all our clients, on using the exponential backoff, are retrying on powers of 2. How can we fix that? What's our go-to solution for synchronized errors? Jitter. So we try adding jitter to the retry delay, and we see that the synchronized spikes are reduced. Another rule for safer clients is to move more control to the servers. Why? Servers are more directly in control of the developers. Bugs are easier to fix, and release cycles for servers are usually a lot quicker than release cycles for client. It's far easier for developers to control servers running in their ecosystem than a client out there in the wild. Safe client behavior, however, is still pretty important, because if the server never got a chance to look at your request, it can't configure the client better or send an appropriate response. On the client side, it's good practice to expose more information to the server. The more a server knows about your request, the more granular a response it can provide. So, if you tag your request with information about the client, like name, version number, or information about the request, was it user-generated? Was it a background request? That can help the server to respond appropriately. User-generated requests can be given higher priority, and in the case of a resource crunch, background requests can be dropped. So far, we've talked about safe client behavior in the context of mobile clients. But what about microservices? Microservices are a system design architecture that lets you break your application into many constituent parts, with each part having its own realm of responsibility. And in order to respond to an API call or a user-generated request, an application can often make many internal microservice calls. Now, the microservice environment is a little different from our mobile client environment. A mobile client can send only up to a few requests per second, and it doesn't really know a lot about the state of the server. On the other hand, a microservice client can send up to hundreds of requests per second, and is usually more aware of the state of the server. In order to have safer microservices, clients should use retry budgets. The number of retries should be limited to a percentage of the total number of requests going out. So, for example, only 10% of your requests can be retries, and all the others should be legitimate requests. This prevents retries from completely flooding out legitimate requests. Another thing that clients can do is use adaptive throttling. Consider a case when a client is out of quota. In that case, it makes sense for the server to drop the request and respond with an out-of-quota error that takes up far lesser resources. But practically, it's not always the best possible solution. A simple RAM lookup can probably take the same amount of resources than sending an out-of-quota error. Also, sending out-of-quota errors takes fewer resources, but it's still some resources, right? Clients can fix that by using throttling. When a client notices that a lot of its requests are being rejected, then it can try regulating the requests that it sends out. Adaptive throttling involves regulating those requests based on the probability of the request failing. So, if a client notices that 10% of its requests are failing, just don't send those 10% requests. Of course, that's an oversimplification, and you can read more about adaptive throttling on this link given below. All right, let's summarize our rules for safe clients. Jitter everything. Don't retry. If you retry, back off. Move more and more control to the server. Expose more information to the server. Use retry budgets. And use adaptive throttling. Thank you. Questions?
Hey, hi, I work at Gojek. So we are also sort of using client-side load balancing and heavy clients to do kind of things you mentioned here, particularly in terms of retries and backoff, all of that. One of the consistent problem that we have faced is basically, let's say, in a normal scenario, a server goes down or something. Now, dynamically, we know the new targets. But how does the client know about which server is overloaded, and based on that, how does that load balancing happen at client, or is that something you won't suggest to do it on a client, but maybe on a server side or behind a proxy or something like that?
Well, it depends on the kind of client you have. So for example, if it's a mobile client, you probably don't want the client to know which of your servers are overloaded. That would doom your company. Any hackers or someone who's trying to DDoS your servers would have way too much information. If it's an internal client or if you're using a microservice, then it's good to have load balancers that act as middle, like there's a middle layer. So the load balancer can know what's going on with all the servers and it can redirect your load accordingly. Does that help answer your question?
Any more questions, guys?
All right, I give you 10 minutes of your life back. Thank you.
Thank you so much, Vanya.